Okay, good afternoon. Welcome to
That's number 942.
942. So I had you read a section in Stephen Strogatz's new book, Infinite Powers, which is a really cool book about the development of calculus. The section I had you read was in the beginning of chapter 3, and I'd like you to tell me what it was about and tell me what you learned.
So it was about how things fall and roll.
Okay. So what did you learn?
So said that this law was, I guess, first it wasn't really a law. It's just like a way things move. But it was first made by Galileo.
Okay. Law discovered by Galileo.
Mm-hmm.
All right. So there was a law discovered by Galileo, and what did it say?
It said that the total distance fallen or rolled is proportional to the square of the time.
Okay. All right. And what were some of the consequences of that?
So he could. Any consequences?
Or what were some of the things in the section I had you read that were the result of the fact that the total distances looks like a square at a time?
And he kind of began to discover instantaneous speed.
Oh, okay.
Which wasn't really something that was looked at in his time.
Okay.
But he sort of began to get a concept or a grasp of the concept, I guess.
Okay. So he began to sort of got near calculus. All right. Now, from the time we spent studying calculus, do you know why total distance? Would you be able to explain using some ideas in calculus why total distance for an object falling or somewhat equivalently rolling looks like t squared?
The total distance is the square of the time. You could take the derivative of this equation.
Okay. Yeah. So
gives an equation for the time.
Well, so the distance, which in calculus we usually call s.
Mm-hmm.
So if this looks like some constant times t squared, do you remember what was the derivative of the distance with respect to time equal?
It's 2 kt.
Sure, it'd be 2 kt. And what quantity is the derivative of distance with respect to time?
That's the speed or velocity.
Yeah, velocity. Okay. So if from calculus, if the speed, the distance looks like the square of the time, a constant is proportional to the square of the time, then the velocity would be directly proportional to the time. And what is the next consequence?
The acceleration. Like if you keep taking derivatives.
Okay, what would happen?
Well, eventually you're going to get down to a constant. The acceleration is a constant.
Okay, so the second derivative of position, which is the derivative of velocity, which is
2k.
There's also known as
some constant.
Some constant. But what is the derivative of velocity?
It's acceleration.
Acceleration is a constant. Okay. And what do we have for objects falling near the surface of the Earth?
Gravity, like 9.8 meters per second squared. That's our acceleration.
Okay. And is it constant?
That's a constant.
Yeah. Roughly speaking, it's a constant. Mm-hmm. It depends on your distance away from the center of the Earth. But for practical purposes, near the surface of the Earth, it's essentially constant. And so, what Galileo was discovering was this in reverse. And how did he do this experiment?
So he set up a ramp, just like a flat piece of wood that was at an angle, and then he rolled the ball down it.
All right.
And he did that again and again. And he varied the height of the ramp and saw how it changed. Then he discovered that this held true.
Okay. Yeah, cool. So we're going to try that. we have a little ramp and we have a ball, and we're going to use one of the ideas from here about it being proportional to the square to see if we can, see if we get a good replication of it.
Alright.
All right, let's do it.